Very good morning, friends. We were dealing with pericyclic reactions. As we know that pericyclic reactions do not have any reaction intermediates and they continuously continue in a single concerted step. These reactions occurs in certain reaction conditions. A diene and a dienophile reaction occurs thermally to give corresponding cyclohexene, whereas it is not possible by photochemical induction. Why is it so? And pericyclic reactions always they give stereospecific products. Diels-Alder reaction, as we see here, it can be induced thermally, not photochemically. Similarly, if I take two alkenes and make it to undergo pericyclic reactions, this is a 2 plus 2 cycloaddition. This reaction cannot be induced thermally to give corresponding cyclobutane. In other words, it is thermally forbidden reaction. However, it can be induced photochemically. In the previous example, we have seen 4 plus 2 cycloaddition is forbidden photochemically, whereas 2 plus 2 cycloaddition is forbidden thermally. Why is it so? Why it follows this specific reaction stereochemically? To explain this, the theory of frontier molecular orbital approach has been put forward by Kenichi Fukai. Kenichi Fukai proposed this molecular orbital theory in the year 1952 to explain the reactions mechanisms of pericyclic reactions. In the year 1952, because of his work and his contribution, he was awarded Nobel Prize in the year 1981. This frontier molecular orbital theory explains whether these pericyclic reactions are allowed under the given set of reaction conditions. These reactions occurs due to the interactions of frontier molecular orbitals. The frontier molecular orbitals may be HOMO, LUMO and SOMO. HOMO stands for highest occupied molecular orbital, whereas LUMO stands for lowest unoccupied molecular orbital. SOMO stands for singly occupied molecular orbital. The interaction of the molecular orbitals, to be precise, frontier molecular orbitals of one molecule with the frontier molecular orbitals of the another molecule gives rise to molecular orbitals of two types. This may be bonding orbitals or anti-bonding orbitals. Bonding orbitals has lesser energy and higher stability, whereas anti-bonding orbitals have higher energy and thus the lower stability. It is the interaction of between these frontier molecular orbitals which dictates with the occurrence of the pericyclic reaction, whether the reaction occurs or not under the given set of reaction conditions. As we have seen, 4 plus 2 cycloaddition is induced thermally, whereas 2 plus 2 cycloaddition is induced photochemically, and vice versa is not possible. To understand this interaction of homo, lumo, and somo, we need to know the concept of phase and symmetry of orbitals. As per this frontier molecular orbital theory, the electrons are considered as the waves. As per quantum physics, the electrons behave as waves, whereas classical physics describe them as particles. But now it is accepted that the electrons behave both as a wave and also as a particle. When it behaves as a wave, the electron's energy, it moves from zero, it acquires the highest position and comes back to zero. This can be one variety of symmetry of orbital that is represented as psi 1. Another way is it starts from 0, reaches the highest and comes to 0, and again through the nodal region it passes in the negative fashion, reaches the highest and again comes back to 0. This can be another phase. This is represented as psi 2. Similarly, it can be having one phase, the second phase and the third phase, which is represented as psi 3. It is this 2p orbital has two different phases. One is the positive phase, another is the negative phase. It is represented as like this. Half is in shaded, another is unshaded. It was represented before as positive and negative. As positive and negative creates confusion as positive center and negative center. Now it is represented as shaded and unshaded. These are the two different phases of 2p orbitals. The orbitals of the same phase, when they combine together, then it is said that they are symmetric in nature. Opposite phase, if they have, they are unsymmetric in nature. It is the interaction of these atomic orbitals which gives rise to molecular orbitals. Let us look into the molecular orbitals of the pi electrons in ethylene in both ground and excited state. The molecular orbitals in ethylene is obtained by linear combination of the atomic orbitals. As we know, ethylene has two carbons and this is bonded with a sigma bond and a pi bond. Pi bond is formed because due to the interaction of pz orbitals that we represent like this. The pz orbital of the first carbon and the pz orbital of the second carbon, when they interact together, it can form the molecular orbital. This linear combination of the two p orbitals gives rise to bonding situation when these two p orbitals are in the same phase. That's why we call this as bonding molecular orbitals. If these two p orbitals are in the opposite phase, this linear combination do not give bonding situation because of the fact that one is in the opposite phase of the other. They are not in the similar phase. That's why it gives a situation where bonding cannot occur. That's why we call it as anti-bonding molecular orbitals. At the ground state, the two p orbitals electrons are having opposite spins, and this is represented as pi, and the anti-bonding orbitals is represented as pi star. As we know that the pericyclic reactions occurs due to the interaction of HOMO and LUMO and SOMO. Here, which is HOMO? HOMO represent highest occupied molecular orbital. Here, in the ground state, the HOMO is the pi orbitals. The LUMO is pi star orbitals. Pi represent the bonding molecular orbitals. Pi star represent the anti-bonding molecular orbital. When there is anti-bonding situation, it is said to be LUMO, lowest unoccupied molecular orbital. Right. In case of excited state, when this electron gets excited, when it is induced photochemically, when gets excited, the one electron which is in the lower energy state will go to the higher energy state. When it is photochemically induced, the highest occupied molecular orbital is pi star. Now you can appreciate the difference. When it is thermally induced, the reaction is thermally induced. HOMO is the pi orbitals, LUMO is pi star orbital. When it is photochemically excited, the electrons from the lower energy level moves to the higher energy level. That's why highest occupied molecular orbital will be pi star. Similarly, if we consider the molecular orbitals of pi electrons of butadiene in ground and excited state, the molecular orbitals and the atomic orbitals can be written as follows. Atomic orbitals of butadiene 1,3 butadiene. The first type of arrangement of the p orbitals are such that all the p orbitals in butadiene is in the same phase. The 1 and 2, the linear combination gives rise to bonding situation. 2 and 3, linear combination can give rise to bonding situation. 3 and 4 are in the same phase, p orbitals. That's why they can also give the bonding situation. That's why 3 bonds can be found here. It is something like 4 friends together, they are moving, they have the same frequency of thoughts. The another phase is the first two orbitals are in the same phase. Second two orbitals are in the opposite phase. Then here, these two atomic orbitals of 1 and 2 position, they can combine linearly to give a one bonding, and 3 and 4, they are in the same phase, that's why it can give another bonding. These are the two process that can occur. It is something like the four friends are together, but they are having the rift. Two in one phase, two in another phase. The third type of arrangement of this atomic orbital is that the first and fourth atomic orbitals are in the same phase. Second and third atomic orbitals are in opposite phase of the first and fourth. Here, these two are adjacent to each other. It can form the 2 and 3 atomic orbitals linear combination can give rise to one bond. It is something situation like this. The four friends are together. The first and fourth run in one direction. Second and third run in opposite direction to first and fourth. The another arrangement of the p atomic orbitals is that the first and second opposite phase, second and third are in opposite phase, third and fourth are in opposite phase. Although they are together, they are still not combined together. All four friends are moving in four different directions. These are the type of arrangements of the p atomic orbitals that can be possible in case of butadiene. The first two orbitals gives rise to bonding situation, more bonding situation. That's why we call it as bonding orbitals. Here three bonds are possible. Here two bonds are possible. In this second, third, and fourth, they are considered as anti-bonding orbitals. In the ground state, it occurs like this. There are two bonding orbitals in which the two electrons are in the two different spin states, and out of these two, the higher energy level orbital is highest occupied molecular orbital. In case of butadiene, the highest occupied molecular orbital is the second one, and the lowest unoccupied molecular orbital is the third one. These four orbitals are given as psi 1, psi 2, psi 3, and psi 4. The highest occupied molecular orbital is psi 2 in the ground state, and lowest unoccupied molecular orbital is psi 3. These are all the possible arrangement of the p orbitals in the butadiene. Out of this, one is HOMO, that is the one which is having highest energy in the bonding situation, and another is LUMO, lowest energy molecular orbital. When it is induced thermally, HOMO and LUMO will be psi 2 and psi 3 respectively. When it is in the excited state, one of the electrons from the HOMO jumps to the higher energy level, and when it is photochemically induced, the orbitals which is considered as highest molecular orbital is psi 3. And LUMO will be psi 4, as the electrons jump from lower energy level to higher energy level when it is induced in excited state. As I said, the reaction, whether it is allowed or not allowed, As I said, 4 plus 2 cycloaddition occurs thermally, whereas 2 plus 2 cycloaddition occurs photochemically. Why 4 plus 2 addition do not occur photochemically? Why 2 plus 2 cycloaddition do not occur in the opposite way? And to explain this, the frontier molecular orbital theory has been put forward. And this, to explain this and to identify the HOMO and LUMO, we have to consider the p orbitals, that is the outermost orbitals, which are involved in the reaction. We have identified the HOMO and LUMO. We have seen atomic orbitals in butadiene and the alkene, various possibilities, and how are they distributed at different energy levels. And in case of, if it is a cyclohexatriene or it is a hexatriene, how the bonding or how the atomic orbitals can be arranged, and how, which are the bonding orbitals, which are the anti-bonding orbitals, and how this HOMO and LUMO interaction occurs will be the subject of discussion for the next presentation. Till then, have a nice day. Thank you.